Hello, Curran here. This video is about how you can effectively use color in data visualization. Here's that slide we looked at earlier in the Marks and Channels video. This is a slide by Tamara Munzner. And I want to highlight that in these channels, there are three separate channels for color: luminance, saturation, and hue. As Tamara Munzner says here, the first rule of color: do not talk about color. It's confusing if you treat color as a monolithic entity, because in reality it's decomposed, or you can think of it as decomposed into three separate channels: luminance, saturation, and hue. The ordered channels of luminance and saturation can show magnitude, and the categorical channel of hue can show identity, just different things. And these three different channels of luminance, saturation, and hue have different properties in what they can convey directly to the perceptual system, your visual perceptual system, and how much they can convey. For example, how many discriminable bins can we use? Here's an example of categorical versus ordered color. In this visualization here, the colors are basically different hues representing years. And even though the years are ordered, the colors don't really have any particular ordering to them. Whereas in this example down here, the colors themselves do have a natural ordering because they vary in luminance. This way of using color is, in a way, more meaningful, more readable, because you can tell that the darker lines represent years that come after the lines that are lighter than those. Here on the right is another example of ordered color, where the darker the color, the higher the value of the sales. This stacked bar chart uses hue for representing various different religions, and it's augmented by this interaction of hovering to highlight the selected regions that match. Note that this doesn't really take advantage of luminance or saturation. It's really just the hue that you can read from here. Here's an awesome example by the New York Times that uses color, hue, for these different ethnicities. With the colors here, you can really see very clear clusters of various ethnic groups in New York City. Here's an example by Mike Bostock that shows the population density in California. And this example really uses luminance to convey density. And here's a similar map for the entire United States. This sort of map where regions have different colors is called a choropleth map. Here's another example of a choropleth map that shows the unemployment rate in the US by county using these various shades of blue. And you could say it uses color, but really what this is using is luminance to encode the data values. But how many shades of blue do you need? I mean, really, how many can you use? In this image here, the first level divides into 2 shades of blue, and then the second level divides into 3, and 4 and 5, and so on. And notice that the further down you get, the more difficult it is to perceive the differences at the edges. And you can perceive all the differences here because they're right next to each other. But as soon as you separate those from each other, it becomes more difficult to tell the difference. Here's a tool I made for comparing 2 different colors. See, if I pick a shade that is more similar to the other one, notice how when you look at it down here, you can tell the difference. You can tell that they're different colors. But when you look at them up here, separated from one another, it's a lot more difficult to tell that they're actually different colors. The point is, when you use categorical color, there's a limited number of discriminable bins, meaning there's only a limit to how many distinct colors you can even perceive. That's because human perception is built on relative comparisons. It's great if color is contiguous, meaning if the colors share a border like this, that means that they're contiguous. If they're contiguous right next to each other, it's a lot easier to tell the difference between two adjacent shapes in terms of their color. But for absolute comparisons, when they are, they could be in any region of the screen, human perception is surprisingly bad. For non-contiguous small regions of color, meaning marks that have colors that are not right next to each other, typically a good rule of thumb is use 6 to 12 bins, and those bins should include the background color and the highlight color. And if you use more than that, then chances are you're not going to be able to tell the difference between certain pairs of colors. On the right, this is an example of a visualization that uses, looks like 20 or 21 different colors. And even when they are like this, it's really hard, for me at least, to tell the difference between this green and this green because they're separated. Maybe if they were contiguous, you could tell the difference. But if I can't tell the difference between the 7 color and the 9 color in this view, how am I supposed to read this view over here? This is an actual scientific paper that was published in 2007. When it comes to ordered color, the rainbow color scale is a poor default, and this is the default setting for a lot of scientific visualization tools. The problem is, perceptually speaking, it's not ordered. You can't say objectively that red is less than green, and it's also perceptually nonlinear. What that means is, if you look at the luminance, it goes from dark to light here at the yellow, and then a little bit darker again, and then light here at the blue, and then darker, and then lighter. See, it goes up and down in terms of luminance. So it's not perceptually linear. The benefits of the rainbow scale is that, sure, fine-grained structure is visible and nameable, meaning you could look at this and say, oh, look at the orange regions. As an alternative to the rainbow scale, you can use color schemes that have large-scale structure and they use fewer hues. For example, this one over here, where it primarily varies in luminance. It also varies in hue, but the primary thing that your eye picks up on is the variation in luminance. And this is more perceptually linear. So in a way, this is a more accurate portrayal of the data at hand. On the bottom here, we have a default rainbow color map applied to what looks like elevation data. And on the right, there's a more well-designed color scheme where the 0 value actually switches. See, at 0 here, there's a break. It's called a segmented scale. And so now you can really clearly read where the coast of Florida is in this. Here's an interesting example that shows how you perceive lightness based on its context, based on its surroundings. Over here on the left, we've got what looks like a white square, and then on the right, we've got what looks like a black square. But if you actually look at them in isolation, they are in fact the exact same color. There's this guy who tweets about visual perception issues, and he's an experimental psychologist, and he studies visual illusions. Here's one of his works, a demo of lightness perception. In the very beginning, it looks like there's nothing under his finger, but as he moves it with his finger, you can see that it's the same as the one in the upper right, and it's also the same as the one in the upper left. It's this slice of the middle. So it's interesting. It just goes to show you, it really depends on the surroundings, the lightness that you perceive. He's got all sorts of these. Here's a demo of the scintillating grid illusion. See how the vertices of the grid here appear to get black if you're not looking directly at them? Here's an example that shows static disks that appear to rotate because of the ordering of the colors inside of them. The relativity that we saw for luminance also applies to hue. See the strawberries here? They appear as though they are red, but it's actually just because they're less green than their surroundings. We can actually, in Chrome, use the color picker to pick one of the reddest looking areas, and see on the right, it's not red at all. It's just more red than its surroundings. He's got tons more of these weird visual perception examples. So many thanks to Akiyoshi Kitaoka for posting these. Next, I'd like to talk about Color Brewer. This is Color Brewer. It's sort of the de facto set of colors that are very well thought out for data visualization. It has a bunch of built-in color schemes, and you can switch between them here to preview what they look like on the map. The one we're looking at here has 3 classes, and you can change the number of classes to see how it turns out on the map. There are also diverging color schemes, meaning the values can go in 2 different directions. This is useful if you've got maybe a 0 baseline where 0 is meaningful and some values are negative, some values are positive. There are also so-called qualitative color schemes where really what's being used here is hue to differentiate between the different classes. So that's Color Brewer. It's been my go-to source for colors in visualization for years now. Next, I'd like to talk about D3 Scale Chromatic. This is a D3 package that has a lot of color schemes built in, and these are mostly derived from Color Brewer, as a matter of fact. The schemes where hue is the real differentiator are called categorical color schemes because they can represent categorical attributes. There are also diverging color schemes, and these come in 2 flavors: an interpolator, which gives you a linear interpolation, but also schemes with specific numbers of different colors, these K values, that can range from 3 to 11. So by specifying various values for K here, it's just like selecting from this drop-down menu the number of bins you have. So these are the diverging color schemes. There are also sequential single hue color schemes. So we've got blues, greens, grays, oranges, purples, reds, and then there's my personal favorite, sequential multi-hue color schemes. Even though these have multiple hues, they are designed to be perceptually uniform, meaning the luminance values vary in a perceptually uniform way. I mean, it's like monotonically increasing as you go from left to right for all of these. So these are the sequential color schemes of D3 Chromatic. Lastly, we do have cyclical color schemes. These are pretty much variations of the rainbow color scheme, but these are actually less angry than the original. Here's a little demo of the original rainbow color scheme, which just varies the hue in the HSL color space. The second entry here is what you get if you vary the hue in the HCL color space. And I believe this last one is what's available in D3. So that's what's there in D3 Scale Chromatic. This is a great way to implement color in visualizations. Practical Rules for Using Color in Charts is a really great piece by Stephen Few. He outlines a couple of rules, like rule number 1, if you want different objects of the same color in a table or graph to look the same, make sure that the background, the color that surrounds them, is consistent. Rule number 2, if you want objects in a table or graph to be easily seen, use a background color that contrasts sufficiently with the object. And rule number 3, Use color only when needed to serve a particular communication goal. And rule number 4, use different colors only when they correspond to differences of meaning in the data. And this one really resonates with me a lot. This bar chart has bars that are different colors, but the colors don't mean anything. To me, this actually detracts from it, makes it confusing to read. I mean, if the colors don't mean anything, you might as well just not have colors at all, or have all the bars be the same color. Here's his rule number 5. Use soft, natural colors to display most information, and bright and/or dark colors to highlight information that requires greater attention. Rule number 6. When using color to encode a sequential range of quantitative values, stick with a single hue or a small set of closely related hues, and vary intensity from pale colors for low values to increasingly darker or brighter colors for high values. This is pretty much saying use perceptually linear color schemes. Rule number 7. Non-data components of tables and graphs should be displayed just visibly enough to perform their role, but not more so, because of excessive salience could cause them to distract attention from the data. And this is why it's nice to use, say, a gray color for the tick marks. And rule number 8, to guarantee that most people who are colorblind can distinguish groups of data that are color-coded, avoid using a combination of red and green in the same display. A lot of people are red-green colorblind. So that's an overview of practical rules for using color in charts by Stephen Few. All right, that's all for using color in data visualization. Thanks for watching. Take care.